All right, hi everybody. Welcome to our Chapter 10 review. This section we're going to be looking at our mole conversion. So everything we've been doing in terms of mass, moles to representative particles, volumes. So everything we can see. So as of right now, we have our mole map. Okay, so mole is the central concept in chemistry for our calculations. So we want to be able to move from moles to either mass or representative particles or volume freely. Okay, so we have our conversion set up in order to do so. So if you remember on your quiz, there are a few different types of questions that we can ask. So let's take a look now at number one at a one-step conversion that we could do. So here we have moles, and I'm going to color code these so that way we know what we're dealing with. So we have moles in purple, right? So remember, moles up here in purple. And we also have molecules. Now, molecules is a representative particle, so molecules are what we want. So to set this up, going from moles to representative particles, we have a conversion of Avogadro's number. So 6.02 times 10 to the 23. So let's write it out. Let's get a different line here. So we have 0.34 moles of CH4 times, now we want to, what do we want on our bottom? Well, we want moles on the bottom, right? Because they will cancel. And then we'll have 6.02 times 10 to the 23 molecules on top. Okay, so that's how we set up our conversion going from moles to molecules. We know that we have 6.02 times 10 to the 23 molecules for 1 mole. And if we multiply our moles by that, we can find out how many molecules there are in 0.34 moles of methanol, or methane, sorry. So let's do this. So we have 0.34 moles of CH4 times 6.02 exponent 23. And that is our answer right here. So we have 2.0468 exponent 23. And because we only have two significant digits given to us, let's just keep this as 2.0 times 10 to the 23. So our answer here for number one is going to be 2.0 times 10 to the 23 molecules. Okay, so that's, whoops, didn't mean for that to happen. So we have molecules of CH4. So that means we have 2.0 times 10 to the 23 molecules of CH4 and 0.34 moles of CH4. So that's just a regular old one-step conversion. Now, if you want to copy this down or rework the question, please pause to do so because I am getting rid of it as of right now. And we're going to move on to something that involves a little bit more work. So two-step conversions. So see you later, number one. We're done with you. Number two, we have grams, and we want to work into molecules. So looking back at our mole map here, when we have mass, which we have up top, mass right here, see how to go from mass to moles? And then we want to go from moles to representative particles again. So we want molecules. So we identify this as a two-step conversion. Okay. So I'm going to color code these again because I think that's a nice idea. That way you can see what's exactly going on. And hold on a sec, I got to make this small. Okay. So if I have 0.98 grams of CH3OH, well, I need to know what my molar mass conversion is going to be. So I need to use my molar mass. So that means I have C times 1, because I only have one carbon in there, H times 3, whoops, this is a common thing to mess up on. So if you write 3 here because you're thinking you're CH3, that's actually wrong because we have 4 hydrogen molecules in there. So it's actually times 4. And then we have oxygen times 1. So let's put some values in here. How do we know what we have for our values? Well, we use our periodic table. So carbon has a mass of 12.01, so we pencil in 12.01 here. Hydrogen, we know that has a mass of 1.01 on your periodic table, but it's too many decimal places on mine, so I'm just going to keep it to 1.01. So times 1.01 is equal to 4.04. And what is it for oxygen? Let's take a quick look here. Oxygen 15.999. And again, because we have different periodic tables, let's use 16. So that's the one that you're going to be able to have at home. So that means that we have 1 times 16.00, and then we add all these up to get our total molar mass. Molar mass is going to be equal to, let's grab our calculator here. So we have 12.01 plus 4.04 plus 16.00. So now we know that we have a total molar mass for this molecule of methanol. We know that's 32.05. So that was the first step that we should have done. 32.05. And that, of course, is always in grams per mole. So now that we have that ready, we're ready to go. So we have 0.98 grams of CH3OH times. Now, what do we want to put on the bottom and what do we want to put on the top for our conversion? Well, we know that we want our units to cancel. So if we put 32.05 grams, our grams here and our grams here will cancel and we will get moles, which is what we want from this step, right? So just to refresh your memory, we're going from mass to moles and then moles to representative particles. So this is the first step. Now, moles to representative particles, I have up here in red. And we want to go, and we use that 6.02 times 10 to the 23 number again. But be careful, we want our units to cancel. So we want 1 mole to cancel out our mole from before. And we will have 6.02 times 10 to the 23 molecules. Okay, so this is 2 steps. We go from mass to moles, and then from moles to molecules. Now let's do a little bit of math here, math magic. 0.98 grams of methanol divided by 32.05, 32.05 down here, and then multiply that by 6.02 exponent 10 to the 23. And I will have, within 0.98 grams of methanol, I will have 1.84 times 10 to the 22 molecules within 0.98 grams. So let's go back here. We'll have the total answer, 1.84 times 10 to the 22 molecules. I'm running out of space. Molecules of CH3OH. Okay. So step 1 in green, step 1 was to find how many moles there are at 0.98 grams of methanol. And then step 2 was to figure out how many molecules there are in that mole total that we found from our last step. So we have 1.84 times 10 to the 22 molecules of CH3OH in 0.98 grams. Okay. So again, I'm going to erase this now, and if you want to pause it, maybe write it down, or if you want anything to do, it's your power. You're sitting at home watching these, so, no pressure, nothing to worry about. All right, now let's take a look at a conversion where we're going from volume to moles, okay? So this is a different one that we have not seen too often. Okay, so we're going from volume here to moles. Now, with volumes, we have these 2 constants that we want to use. So 1 mole is equal to 24.8 liters at SATP, so standard ambient temperature and pressure. And 1 mole at STP is equal to 22.4 liters. So we don't really need to know a whole lot about why or, a whole lot about these STP and SATP at this point, but we do need to know that they are equal to 22.4 liters and 24.8 liters respectively. Okay. So now that we have our 20.1 liters of nitrogen gas, so N2 gas, and this can be at any gas. So 1 mole of any gas is equal to 22.4 liters. at STP, and 1 mole of any gas at SATP is equal to 24.8 liters. So this could be chlorine gas, or it could be methane gas, or it could be, something festive like candy cane gas or Santa gas. Doesn't that sounds funny? But any sort of gas that we're dealing with. Okay, so we need our conversion factor to move from volume to moles. So we're going to deal with that now. And what we want is moles. So we always want to put what we want on top because we want moles. And that means that we have SATP here, so we need 24.8 liters. Okay. Most students will get that mixed up between 22.4 and 24.8. Just remember to carefully look at what the conditions are in your problem. Okay, so these ones are really the most straightforward conversion that we have. So these liters cancel, and now we're dealing strictly with moles. So we have 20.1 liters right here, divided by 24.8 is equal to 0.8104 moles. So we were given 3 significant digits, so we can only report in 3, so let's leave it at 0.810. So this is equal to 0.810 moles. Okay, and that mole of N2 gas. Okay, so these ones look a little bit more, I don't know, more intimidating because you have something like a variable you don't know much about here. But in reality, it's the easiest conversion because it's either SATP is equal to 24.8 liters, or STP is equal to 22.4 liters. Okay, so this is our final answer here. All right, so like I said before, you can pause right now if you wish to write this down, or I can just, talk you through me erasing it. Okay. Okay, so let's take a look now at a 3-step conversion. It's number 4, but it's not a 4-stepper. So here we go. This is probably the biggest question you can have in terms of mole conversion, and this will definitely be on your test. So we have 13.0 grams of barium hydroxide. We want to know how many ions we have. So the first step is to find our molar mass because we're given a mass of barium hydroxide and we're going to need it to convert into moles, right? And then we're going to go from moles to representative particles, and then we have formula units, which is our representative particle, and then we need to get that into ions. So don't be worried. First step we need to do is molar mass. Let's break this down step by step. So let's find out what the molar mass is. So we know we have barium, and that's going to be 1 times, let's find out what barium weighs in terms of its molar weight. And barium is 137.33, so we have 137.33. And we have oxygen equals 2 times 16.00. So over here we have oxygen at 15.999. However, on your periodic table back home, it's going to say 16.00. And then hydrogen is going to equal 2 times 1.01. 1.01. Okay. So let's get rid of my periodic table. All right, so let's do a little bit of math and add all these up. So 137.33 equals 32.00, and hydrogen is going to equal 2.02. So let's take my calculator. We go 137.33 plus 32 plus 2.02, and that is going to equal too big. What did I do? This is showing just how careful you really have to be when you're adding up your molar masses, right? So I goofed, but it's a good goof to show you exactly what went wrong. So now we have 171.35 grams per mole. 171.35 grams per mole. Okay? So now we have our molar mass, as it says up in our mole map, that we need from mass to moles. So let's set it up. We have 13.0 grams barium hydroxide times. What do we need to put on top and what do we need to put on bottom? Well, we need our units to cancel. And here we want moles and we have grams. So we have the molar mass of barium hydroxide. So now our grams will cancel, and we need to move into our next conversion. And our next conversion is going from moles to representative particles. So what we need to do is we need to multiply this by 6.02 times 10 to the 23. And this is an ionic compound, right? So we have a positive ion and a negative ion. So in an ionic compound, they're actually called formula units, just in case we didn't know that back home, right? So it's really good to label all of this stuff, so that way your units will always cancel, as they do here. We have moles on the bottom because we wish for them to cancel from the moles beforehand. So now we're dealing with just strictly formula units, but the question's asking us for ions. Now if we look back all the way up here in our mole map, you'll see that formula units to ions also requires one more conversion factor, okay? So we'll do this one in black. And let's get rid of our periodic table here. Oops. So now we want to know, hey, how many ions are there in one formula unit of barium hydroxide? Because there's one barium and there's two hydroxides when you think about it like this. Okay? Barium, hydroxide, hydroxide. So that means that there's 3 ions per one formula unit. So we put 3 ions per one. I'm going to write F-U because I'm running out of space. But you can see we write formula units on the bottom, so that way our formula units will cancel. Okay? Now what are we left with in terms of units? Well, we don't have grams anymore. We don't have molecules anymore. We don't have formula units anymore. We have ions. And guess what? That is what the question's asking for. So that's perfect. Now that we set it all up and your units are all canceling, and by the way, that's the easiest way to see if you're doing these right. Let's multiply it all out. 13.0 grams divided by 171.35 grams per mole times 6.02 exponent 23 times 3 ions, and that's going to equal 1.37 ions times 10 to the 23. So our total here is 1.37 times 10 to the 23 ions. And that's how many ions are in 13 grams of barium hydroxide. Okay, so I'm going to leave that up there for a second. You can copy that down. I'm going to erase. So just to give you some, general information about the test tomorrow, we need to always know how to set up our conversions, okay? So a lot of people during the quiz were giving me, not showing a lot of work. And for these, it's really crucial to show your work, so that way you can always see what units will be canceling, okay? So study hard, give these a couple more tries, maybe watch the video again if you need to, and good luck tomorrow.